Hey there, math fans. Dr. Andy Loveless here. I'm going to talk about polar curves. That probably doesn't sound that exciting, but I've taught, if you don't know me, I've taught math at the University of Washington for 20 years, taught over 21,000 students. And we always cover polar curves. It's kind of dry and boring. And so I thought, hey, I'll just sample a few interesting things from polar. For my students, this is not something I'm testing you on, but maybe this would get you interested about what you're doing. So I'll show you some visuals. I will take you through some names and say a few things. And I don't claim to be an expert. I always like to say that I'm trying to prove I'm not very smart, and it's pretty easy to do. So polar is really good for circles or things that spiral because it describes the distance from the origin. A circle centered at the origin is really nice, but you can get other circles. So a challenge for my students is try to take a circle centered somewhere else of a given radius and find the polar equation for it. It's not that pretty if you get it in general. I actually had never done that before till just now before this video in order to make that picture that you're seeing in the corner. But I did make it, and I was able to play around with it a little bit. So let me show you that. So I made it so I could move this around. So I had to do some solving to get it. It gives you a big mess. Okay, so let's move on to the next type. I had to look up the pronunciation. It's French. Lemicon. So if you don't know who Pascal is, famous mathematician, his father studied these shapes. So this is that. And then later someone named him after a snail. I guess that's what lemicons means. So I must have thought it had a snail shape. So these are them. So I'm calling it Pascal's father's snail. I like to look up a little history to try to really put my students to sleep. So here it is. I've made it so that I can move it around a little bit. It's this equation. So if you think about the distance from the origin, if I make this a 0 here, I can't get it. I can't quite land it. Okay, there we go. Then R is 1. If you walk around that, think about your distance from the origin. It's always 1. Always 1. So you're on a circle. If I change it, I'm changing this parameter, the number in front of cosine, to something else, like 0.5. Now think about what happens. If you plug in 0, you get 1.5. If you plug in pi over 2, you get 1. If you plug in pi, you actually get a half, so it's smaller. So you get this unusual shape. If you keep going, you get this dimpled shape. Like this. You can see that little thing coming in. And there's an interesting spot when you get to the coefficient being 1. Here we go again. Not watching this guy's videos. He can't even click on 1. Okay, so here you go. If you plug in pi here, you get a 0. So if you think about going around this is more for my students, but I'm going to show something here that I think is worth us chatting about. But you should see, I wanted to get rid of that the distance from the origin, as you move around this thing, it's 2 initially, and then it's 1, and then it's 0. The moment you make that 1, you might try to guess what happens if you make the coefficient in front of cosine bigger than 1. That means when you plug in pi, you're going to get a negative. And it spirals back through. And you get this weird shape. Okay, so that's a whole collection of things you get, but it's just an opportunity for you to think about distance from the origin. That's kind of fun. Okay, this special one, when it just touches in the middle, is a very important shape. It comes up a lot in various applications, so I'm going to say a few things about it. That's called a cardioid. It looks kind of like a heart. So that's this one in the middle here. There are a bunch of places you maybe have seen that shape besides it just being a heart. If you take light and put it against a coffee mug, you get this little shape here, like how the light comes through. You also, I kind of famously get it at the corner of a clock or a watch because the way the light comes over the edge. So it's a geometric thing. When you get a coffee at the store, it is kind of a heart shape. I guess it's not quite a cardioid. It sort of looks like one. This so-called Mandelbrot set has a cardioid in it. You can see it right there. So just a shape we sort of like. Comes up in a lot of places. Okay, next, so that's why those get names. It's basically like a squished circle. So you have circles, you have squished circles. And then really squished circles, so much they squeeze through. That's what my spine looks like, according to my back doctor. That's my my vertebrae coming out. Not my vertebrae, my disc. Okay, so then there's roses. And so I showed you the equation for one of these. This is like 1 plus 1 cosine of theta, now that we've talked through it. And those ones I was showing you were just different values in these two spots. Okay, so the roses look like this. I was looking this up. I hadn't seen this name, but this is called a quadrifolium. And it's R equals, I didn't make up the names, don't get mad at me, cosine of 2 theta. And this was a trifolium, which is cosine of 3 theta. They call it a rose because it has these petals. The reason it does this is because R equals 0 at various angles. And that makes it pass through the origin. If this is even, you actually have twice as many petals. So if it's 2, you have 4 petals. If it's 4, you have 8 petals. If it's odd, you get the same number of petals. It just has to do with really when R equals 0. An interesting couple things I want to show here, just as I did a tiny bit of research, and hopefully I haven't put you to sleep already. I already showed you that one. This is not polished. Who would watch this guy? Okay, here we go. We're watching this. Here it goes. So that's with the 2. I got it so I can tweak things around. There you go. If you want something polished, go somewhere else. But if you want to learn a little bit of math, come back and ask me a question. So there you go. There's a few examples of the rows. Okay, something I wanted to show you here was this. So first for the cardioid, I forgot to show this. If you put a little pebble on the edge of a tire and roll it around a circle, you get this shape. This is sort of famous in that if you roll a tire along the ground, you get this important shape called a cycloid, which comes up in all sorts of things, the fastest slides and things like that. The rose comes up, and sorry for the text there, the rose comes up in gear discussions. So if you have gears that are connected of various shapes, and you have something going back and forth, so you could imagine these things come up. The one you're actually seeing, one is just a circle. The next one is actually an example of a, I forgot how to say it, Lemicon. And then the next, here you have one of these trifoliums, now that I know the name, and here you have a more exotic thing. So these shapes you can kind of generate from a gear system, which is kind of interesting, but also if you're working with gears, it might be something you need to know. Okay. The next one's kind of a special one called a lemniscate. That's actually a word for anything that looks like an infinity symbol. This is the Lemniscate of Bernoilli. Boy, I can't say any of the words right. But it comes from a polar equation for the distance. Again, all of these are just equations that come from different descriptions of your distance from the origin, R being your distance from the origin. So they're spirally things. So that's what you get. I looked this particular lemniscate up, and it has this property that has to do with tangents that Bernoulli studied. And lemniscate means ribbon or decorated with a ribbon. More useless facts. Okay, and then spirals are kind of interesting. So if you have R be some number times an angle, that gives you a spiral. As the angle gets bigger, you also get further away. Now, this is just a cool one that I pulled up from Wikipedia, spiral of a nebula around some star. I don't know anything about that, but I thought it was an interesting picture. Let me show you a couple of these things, and then we'll finish with a chance to just explore, because I really do think that a lot of this is just a way you could be really creative on your own. So there you go. There's that equation. Working with a formula that measures your distance from the origin is a new type of art for you to think about. So there you go. There's a spiral, right? Playing around with the number in front of theta. There are, like, the classic shapes can be described, but they tend to not have nice equations. The conic sections, the hyperbolas, the parabolas, the ellipses. This is important because this is something that Kepler used to prove that in order to prove the orbits of the planets were an ellipse, he did everything in polar. And so the end result of his work was that he got this polar equation, which looks really weird, but it's equivalent to an ellipse. I don't know anything really about that. That just is in one of our calculus books. Again, I'm not smart. You don't have to be smart to do math. You might say, well, do you really do math? You just teach all the time. Ouch, that hurts. All right, let's finish up here on this last thing. So then I just thought, let's just be creative. So I looked through lots of examples. Sine and cosine are nice because it keeps you from spiraling away from the origin. They are stuck between 1 and -1. So I just made one up. So I don't know what to call this. What I like to do if I'm trying to do art in a graphing calculator like this is I take something that's sort of like something I know, and then I throw in a bunch of parameters in Desmos, and then I mess around with those parameters. And then I try things. It's an interesting little experimental thing. So I'm calling that Dr. Loveless's big head angel. But I'll show you what I actually did is I allowed it to scroll through different numbers in place of, I think, that 3. So here's here's where I started. Was just scrolling through whole numbers. But actually it gets pretty interesting if that's like a weird butterfly. I also like that one. I don't know what to call that. Dr. Loveless's unusual butterfly. Okay, those are kind of cool. If you allow fractional numbers, it gives you more of a continuum of things, and it's spectacular. And then I was like, what can I do? So then I shifted it a little bit, and just a little shift makes it pretty cool looking. I mean, look at that thing. You don't have to be smart. So we'll finish with them all, but I will do a couple things here. I'm just playing around with different values of sine and cosine. You can be adventurous with math and not have to be smart. I prove it every day. So that's pretty fun. Spiraling around. Let's make it go a little faster. Here we go. Why do I like this so much? What's wrong with me? What is going on there? It's like what my stomach feels like after eating at Taco Bell. Look at that one. Ooh. So go explore, grab Desmos. If you want, you have to put a comment on my video. You have to subscribe and like. Then I will share this Desmos with you, and you can play your own game. This is what my head feels like after a day of teaching 480 students. All right, here we go. Let's see what else we can do. I got to end this video, I know. I'm working all day on other things. Holy smokes, what's going on here? That's kind of fun. What else can we do? Let's make this go much higher. And this is when my instructor lost his mind. Just playing around with our distance to the origin. And if I change any of these numbers slightly, you can get more exotic things. All right. So enjoy, go explore. I'll keep exploring here. Please, like and subscribe. Give me comments. Give me some encouragement here to show me what I'm doing is worthwhile. Appreciate all of you that have helped me take these moments where I can just explore something. All right. Take care.